My name is Rick Pires, and you want to introduce yourself? You sure? Try it.
My name is Miranda Pires.
And we're going to be doing a demonstration today that I've called The Power of Swedish Fish.
Actually, to be technically correct, the title should be The Energy Contained in Swedish Fish, but that doesn't sound nearly as dramatic.
What we're going to be looking at today, if you could, thank you, is a fairly interesting reaction. And the reason that I say it's an interesting reaction is because in some ways it's related to a reaction that all of us do every day. We're looking at reacting sucrose, which is table sugar, with an oxidizing agent. And this is very similar to the reaction that takes place in your body whenever you eat anything with sugar in it. The difference today is that we're going to be releasing all of that energy all at once, whereas your body releases it a little bit at a time. And we could use a bunch of different sources for sugar for the sucrose in today's experiment. Do you want to read those, Marina?
Sucrose, sugar,
We could use table sugar.
brown sugar, maple syrup, or a type of candy like candy corn.
What we're actually going to use is,
Swedish fish.
and I've got them here. There's actually a lot of sugar in these Swedish fish. Each one, where did you put them, Miranda?
Down there,
Ah, actually, it's right here.
right there.
This is the oxidizing agent, the KClO3. This is a Swedish fish. There's about 4.5 grams of sugar in each of these Swedish fish. So we're going to do the reaction in a minute, but I want to talk a little bit about how much energy is in there. I tried to compare it to something that we're all familiar with. And I did a little bit of a dimensional analysis to look at that. And not going through the details, I compared it to gasoline. And what I said is, if you had a car that got 30 miles per gallon, it would take about 56 Swedish fish to run your car for 1 mile. Now, I don't know why the EPA doesn't switch to this as a fuel standard. They're not returning my emails about this, but as one of my colleagues put it, that means the next time you eat a Swedish fish, you have to push your car about 100 feet to burn off the calories from that. So there's a lot of energy in the Swedish fish. So we're going to add the Swedish fish now. And actually, there's one more slide before we do that. Another way to look at it, the way that you looked at it in Chem 101, is that the reactants are higher in energy than the products. They're higher in energy by 6,010 kilojoules. So when we do this reaction, we should give off a lot of energy. And we're going to see that happen now. Where's that fish I gave you?
I ate it.
Oh. You ate it?
Yes.
Okay. Don't eat this one. So we're going to add it, and hopefully I can keep this under the camera while she adds this. And it didn't react. Still doing nothing. And actually, you want to chew this now? Actually, I like to do this demonstration at the beginning of Chem 102 because it shows the difference between Chem 101 and 102. In Chem 101, we look, if you can go to the next slide, we only look at the beginning and the end of the reaction. We look at the reactants, we look at the products. We say the reactants are higher in energy than the products, so we should get off a lot of energy. What we don't look at is what happens in the middle. And it's what happens in the middle that you look at in Chem 102. And what happens in the middle is that you have this barrier that the molecules in the Swedish fish have to get over before they can react. And it's this barrier that's stopping them from reacting. So we need to do something to get the molecules of sugar in that Swedish fish over that barrier. And there are a few things that we could do. We could lower the size of that barrier, and that's what a catalyst does. It lowers the size of the barrier, and the enzymes are catalysts. They lower that barrier. We could also raise the energy of the reactants. It's a little bit harder to do. Some enzymes can do that. What's easier for us to do is to provide the molecules with more energy so they can jump over that barrier. And simply put, we could heat it. What that does is, if we look at what's labeled as T1, only a few molecules have enough energy, if I get the laser pointer here, to get over the activation energy barrier. Only the molecules in this shaded area. When we heat it up, more molecules in this pinkish shaded area have enough energy to get over that barrier. So when we heat it to a higher temperature, enough molecules can get over the barrier, the reaction goes a lot faster. And that's what we're going to do with our Swedish fish right now. So let me get out a source of heat. Here's another Swedish fish. Maybe later. And are you going to add the fish? It's gone again? Okay. Don't eat the next one, please. Okay, so let me get this ready. I'm going to point it this way so we don't spray the crowd. Turn on my heat source. It's going to take a few, I was going to say a few minutes, but it's not going to be a few minutes. 30 seconds or so to get this warm enough. We really want it to be melted so that it actually coats the whole fish. So I'm melting the oxidizing agent right now. I got to be careful not to get it too hot because its decomposition temperature is not too far above the melting temperature. Okay, we're just about there. And when I shut off the flame, you're going to add the fish. Okay, let me shut it off first. Add it. Try to cover it now. So I think I'm going to put out the last little bits so that we don't fill the room too badly with smoke. And I've got something to cover it here. But you can see how much energy is stored in those Swedish fish. So next time you eat some of them, make sure you go and push your car. And that's it.